This is an exciting day because we are going to start talking about proof and reasoning. And it's one of the most unfamiliar things we're going to look at this year because it is such a departure from what you are used to studying in math or even other areas of your school academics. But it is a very important part of mathematics, and any class that you take beyond this class in math will incorporate elements of proof or reasoning in some way. So it is the job of the geometry teacher to initially introduce you to these topics. You may have done a little bit in algebra last year, but we're really going to look at this from a structural point of view now and really build this up as a complete understanding of what proof and reasoning means. So I want to start by talking about two kinds of reasoning. We have inductive and deductive reasoning. And these are opposites of each other, but they're both used in math. So we need to describe the two differences here. Okay? So inductive reasoning means that you look for a pattern and then try to generalize. You don't know 100% certainty that the pattern will continue, but you make an assumption that it will. So you're looking at information that you have, whether it be data or given information, and you're looking for patterns. And then based on those patterns, you try to generalize what the patterns are telling you. Now, you don't have 100% certainty, so I want to say that again. You're not 100% black and white certain that the pattern is going to continue, but based on the information you're given, you make an assumption that it's going to continue. And when you do make that assumption, it is called the induction assumption. Okay, and we're not going to do a lot of this in this class. It's a little bit difficult, more difficult to do than the deductive reasoning, and so usually you end up learning about inductive reasoning when you are studying something called discrete mathematics in college. Okay, so to generalize this, you're taking a pattern and generalizing it. Now with deductive reasoning, you start with facts, and from them you figure out or deduce some more facts. So this is starting with facts and figuring out more facts. So you have facts lead to facts. Okay, this is what we're going to be doing in geometry this year. But I just want to clarify that both are valuable methods of reasoning that are used for proving things in mathematics. And some of these examples today in this video are from the 2005 edition of the Geometry book by Glencoe. We have these at school. We own a class set of these, and I use them occasionally. I don't use them for very much, but some of the examples today I pulled from that textbook. I used to use them before I wrote all my own notes. So let's talk about some definitions. We need to really set up these definitions so we can understand what we're talking about here. A given is simply a piece of information that is given to you and it can be assumed to be true. Always. It can assume to be true. Okay? A conjecture is an educated guess or prediction based on given information and known theorems. When I say known theorems, I'm just talking about other theorems that we know to be true. So like we all know that the Pythagorean theorem it says what it says, and so if we needed to use that to make a prediction, then we could say, oh, well, by the Pythagorean theorem, we're basing our information off of that. So it's either based on given information or other theorems that you know. Now, a counterexample is simply an example of something that disproves a conjecture. Okay, it disproves a conjecture. So you may notice that it does not disprove a given, because again, the given can always be assumed to be true. Okay, so you're not trying to mess with a given or trying to disprove a given. But if you're making a conjecture, which is an educated guess, right, and then you provide a counterexample that disproves that conjecture, then what it's doing is it's showing that the conjecture was not correct. Okay? And you only need one counterexample to show. I'm going to write this in red so that you don't, or green so that you don't forget it. You only need one. Okay, you only need one of these. If you can show one counterexample that disproves a conjecture, then that's all you need to show that the conjecture was false. A negation is where you take a piece of information and give the opposite. And I'm going to use this word opposite in quotation marks because it's not really the opposite. Usually we think about this and we say, well, if there is a given piece of information, the negation of that is we find the negation by using the word not, and we also use this symbol, which is a tilde just by itself. Okay, that's the symbol. So if the given information is that it's sunny outside, the negation of that would be that it's not sunny outside. Okay, so it's not really the opposite, but you can kind of think of it as the opposite. But just remember, I'm putting this in quotation marks because it's not actually really the opposite. I'm just kind of using that as a figure of speech. Okay, a compound statement, you're familiar with it from science class. It's an if-then statement. So you say if something, then something else. And we're going to start calling these specific things as parts of this. This first part is the hypothesis, and we usually use a lowercase p to designate that. And after then comes the conclusion, and we use the lowercase q to denote that. So you might say a compound statement would be like if, let me just grab a pen here. Okay, so what if we say like if it's sunny outside, then it's daytime. Okay, I have an idea. Let's look at this. If it's daytime, let's reverse this. Okay, I'm just going to reverse this. We'll learn in a second what that's actually called. So let's say if it's daytime, then it's sunny outside. Okay, if it's daytime, then it's sunny outside. So in this case, this is the hypothesis. Okay, that's P. and this is the conclusion. Okay, P and Q. If it's daytime, then it's sunny outside. Of course, we could come up with a counterexample, and we could say, oh, but what if it is what if it's cloudy? It can still be cloudy during the daytime, so this would be a counterexample that disproves this statement, okay? It would be a counterexample of what we need to be true. Now, I want to talk about 4 different kinds of conditional statements that we're going to be learning about here. So, remember that the basic structure of a conditional statement is if-then. If P, then Q. Or if hypothesis, then conclusion. And so the conditional is that base statement, if P, then Q. And the symbology we use to write that in math symbols is right here, P, arrow, Q. Okay, so that is the way we write it using math symbols, if P, then Q. The converse happens if you take P and Q and you flip them. You flip the position. So then you have if Q, then P. Okay, and remember that now P is the conclusion and Q is the hypothesis. The hypothesis is always with the if. Okay, this is always the hypothesis and this is always the conclusion. But these are just our statements. These are P and Q, and I'm just taking them and I'm flipping them around. So going back to my statement right here, if this is the conditional, then the converse would be if it's sunny outside, then it's daytime. If it's sunny outside, then it's daytime. So what I did here, I just took these and I reversed them. So whereas this, as it's given the conditional, we have a problem with it because what happens if it's cloudy? If I reverse it and do the converse, if it's sunny outside, then it's daytime, that's always going to be true. So the converse in this case is true, the conditional is not true, it's false. And so we would write this just by reversing the order, we would write this like that. Okay? Similarly, we have something called the inverse, which is where we take the negation, remember the negation up here, by putting the not in there and the little tilde, the negation of both P and Q in the original order. Okay, so we're not changing the order yet, we're just leaving it if P then Q, but we're changing them both to not. So if not P, then not Q. And so we write that with our little tildes in here, just like that. And finally, number 4 is the contrapositive, which is a cool name. And that is where we flip them and do the negation. So if not Q, then not P. Okay, and we're going to learn a lot more about these kinds of things, but we're just going over the basic definitions right now. Okay? So more definitions right here. More definitions. A conjunction is an and statement. This is an and statement, okay? And the symbol is this little V that looks like it's pointing up. It's actually a big V, okay? And this is where you can take two different things and combine them with and this means both. This means both. So if you're saying something and something else, then they both have to be true for the conjunction to be true. We're going to work through an example in just a second on this, okay? A disjunction is an or statement, kind of similar but kind of different, and the symbol is the inverted version of that, and this is an either statement. So if you have something or something else, then you can take either of them, but you don't have to have both, okay? If you had a choice between I don't know, chocolate ice cream and vanilla ice cream, and somebody said, oh, I want chocolate and vanilla, then that means you want both, right? You want both kinds of ice cream. But if somebody said, I want chocolate or vanilla, then that means you're willing to take either. You'll have one or the other, but you don't want both. I'll have chocolate or vanilla. Okay? It means you'd be okay with either one. The truth value is the true or false nature. So this is true or false nature of a statement. Okay? The true or false nature of a statement. Not to be confused, let me write this out right here. Not to be confused with validity. What is validity? Something that is valid, right? Not to be confused with valid, because you can have you can have a valid statement that is false. You can have a valid statement that is false. If you've constructed it validly and you followed all the definitions I'm teaching you and everything else, you can have, here's an example, you can have a conditional statement like this one right here. If it's daytime, then it's sunny. I've constructed this just fine. I have a hypothesis and a conclusion, nothing wrong with this, so it's a valid statement, but it's not true. So don't confuse this with validity, okay? All right, biconditional. This is a really, really neat one. Biconditional is what we call in math if and only if. And the symbol that we use for this is IFF. Well, lowercase IFF. So it looks like the word if, the regular word if, but it has two F's in it. So it looks like you made a typo, but actually you didn't. So IFF, okay? And that's how we write that. A biconditional is a statement and its converse that are both true. So if or I should say if a conditional. If a conditional statement and its converse are true, are both true, then we say it's a biconditional. And write P and double-headed arrow and Q, like that. This means if you can go one direction, you can turn around and come back. So if you think about it, you're going this, you can go this direction, or you can turn around and come back. So two-way, biconditional. Okay, we'll learn more about that in class. A few other symbols that are used when we're doing these kinds of things. You're not going to need to know these three down here, but I put them down here anyway. 3 dots like this means therefore. 3 dots upside down like this means because. And a little square means quod erat demonstrandum, or QED. This is Latin, which says that which was to be demonstrated. And this is what you write at the very end of a proof. And so usually in mathematics we use a little square. In physics they write QED. You can do either one, they mean exactly the same thing. And we'll see this when we start actually constructing some proofs in a few days. An upside down capital A means for all. A backwards capital E means there exists. And then this lower case little curvy looking E, which is actually a Greek letter epsilon, means something is an element of something else. These are kinds of things we're going to be you would use more in like higher classes. So you don't really need to know these, but I at least wanted you to see them so that when you see them later, you can think back. Oh yeah, Alex mentioned those. Let's look at some examples. If the given is that point C is the midpoint of line segment AB, now remember, this is a given, so you just assume that this is true as can be, okay? If point C is the midpoint of AB, well, let's draw a diagram that demonstrates this. Okay, so if point C is the midpoint of AB, then that means we have some line segment here, and it's A, B, and then right in the middle somewhere we have point C, okay? And if it's the midpoint, then that segment is congruent to that segment, right? Then our conjecture is, what could our conjecture be? Our conjecture is that AC is congruent to BC. Now, notice the difference in what this is saying. You may have already jumped to this conclusion and said, well, of course AC is congruent to BC, but that is not what the given is saying. This is exactly what the given is saying. And so if you can make a conjecture that is different or some kind of an application of what the given is saying, then it is a different statement, okay? Notice that what is given is literally saying, and that's why I'm boxing it in, this is exactly what's given. Point C is the midpoint of AB. That means that we have a line segment and C is at the midpoint, and then we can use the definition of midpoint. So we're using the definition of this word to then determine that AC is congruent to BC. That's really all we're doing. So don't make this out to be harder than it is. But you have to be careful. Whatever the given is saying is exactly what it's saying. And if you want to extend that and make it do something else, then you have to deduce that statement using deductive reasoning. That's why we're doing this. Angle 1 is the complement of angle 2, and angle 1 is the complement of angle 3. Complement means that the sum is 90 degrees. So if angle 1, let's just look at this. Let's say, okay, so let's say something like this. Okay, and let's just do it like this. Okay, so let's say that this is angle 1, this is angle 2, and this is angle 3. Okay, so if angle 1 is the complement of angle 2, then that means that these two together equal 90 degrees, right? And angle 1 is the complement of angle 3, so that means that angle 1 and angle 3 have to be 90 degrees. So what does that mean? What does that mean about angles 2 and 3? That's what our conjecture is going to be, is that angle 2 has to be equal to angle 3, or congruent rather. Because if I'm saying that, angle 1 plus angle 2 is 90, and I know that angle 1 plus angle 3 is 90, then obviously, just using our algebraic properties that we know, angle 2 and angle 3 have to be the same, right? They have to be the same. So that's what our conjecture is. Now I mentioned this over here on the side. I just want to look at it real quick. What type of logic is this? Well, this is inductive reasoning, and so is this. Because you're not given the diagram, you're not told that these are congruent, you're told something else. So you're trying to take this information and determine what it's saying and then generalize what it is saying. That's what we're doing with this. And the same thing down here. Okay? Now, here's another example. Let me draw this line just so we're clear as to where this ends, because I've kind of messed it up there. Okay. Okay, we have four statements. Statement P is -3 minus 2 is -5. That is obviously true, right? That's obviously a true statement, so I'm going to just mark that right here. That's true. We also know, and I'm actually going to mark this in blue just to make it really clear as to what I'm saying here. That's true. Okay. And then vertical angles are congruent. We also know that that is true. Okay, those are both true. 2 plus 8 is greater than 10. That's obviously false because 2 plus 8 is equal to 10, not greater than. Okay, and then the sum of the measures of complementary angles is 90. By definition, that is true. So we have 3 true statements and a false statement here. So determine the truth value of the following: P and Q. Okay, so P and Q. This means both. Both P and Q have to be true in order for this to be true. So P and Q are both true, so P and Q as a conjunction is true. Okay, that is, whoops, I hit my 3-hole punch there. Okay, that is true. Okay, what about P and R? Well, if they both have to be, and this is again a both statement, they both have to be true. P and R is not true. So just because R is not true, then this whole thing is not true. This whole thing is false because it has to be a both statement here. Now here is an or statement. This is an either. If either of these is true, then the whole thing is true. So P or S. P or S. In this case, they're both true. So we can say that this is true because either one of them is true. What about R or S? Well, this is again an either statement, an or. Either. Okay, either. Okay. R or S. R or S. Well, R is false and S is true, but since it's either that we're looking at, then this whole thing is true. Okay. What about this one? Not Q. Well, if Q is true, then not Q has to be false, right? So here we're looking at P, which is true, and not Q, which is false. But since this is a both statement, then this whole thing is false. This whole thing is false because they both have to be true, and not Q is false. Q and not R. Okay, well, not R would be true because R was false, so not R has to be true. Q is already true, so true or true. This is an either, but in this case they are both true, so this is going to be true because either one of them was true.